The problem we are trying to solve is the growing population of lionfish in the Atlantic seaboard. Lionfish are native to the Indo-Pacific Ocean and were brought to the United States because of their attractive appearance. However, as lionfish are not easy to keep in home aquaria, many have been released into the waters and are now an invasive species in the Caribbean Sea and east coast of the United States. Since lionfish were brought here from the Indo-Pacific Ocean, they lack any natural predators. Currently, the only viable solution is for scuba divers to hunt lionfish manually. However, this is inefficient as a female lionfish can lay up to 2 million eggs per year, and human divers will not be able to stay underwater long enough or reach enough marine areas to negate this growing population.
To address the problem of underwater time, mobility, and depth, we are developing an autonomous underwater vehicle, or an AUV, to hunt and collect lionfish.
An important capability for the robot will be to determine the distance between itself and various objects in the environment. By using 2 cameras mounted on the front of the robot, we can extract depth information using a process called stereo vision. Much like how the human eyes work and are able to judge distances, stereo vision works by comparing the images captured by both cameras. The distance of an object can be determined by using the algorithms which compare how different the object appears from one camera to the other.
To capture lionfish underwater, the robot has to be able to perform basic navigation functionalities such as diving, ascending, turning, and driving straight underwater. Using the built-in functionalities given to us by Blue Robotics and PID control, we were able to achieve reliable diving, ascending from and to a depth, driving straight, and turning to a given angle with an error of plus or minus 5 degrees.
To protect the electronics in the underwater environment, our electronic components are sealed away in a pressure chamber, and sealing the chamber can take up to an hour. During this time, the batteries are still discharging, so we added a power switch that turns on the robot when a magnet is brought near the chamber and turns off the robot when the other pole of the magnet is brought near. This will help by allowing us to not need to open the chamber between running the robot on the same day unless the batteries need to be recharged.
The robot needs to collect multiple lionfish on its patrols, requiring an onboard containment system. Previous designs have been relatively unwieldy, causing large amounts of drag due to solid walls and oblique shapes that jutted out from the robot's main chassis. A new design was developed that maximizes carrying capacity while reducing the front and side profiles of the robot, reducing the drag as much as possible. The new container also features a mechanism to ease the removal and retainment of captured lionfish. We hope that the improvements this year can excel this project